All right, so today we're going to talk about optical spectroscopy and introduce surfaces and their role in the optical characteristics of nanoparticles. First, I wanted to review some of the things we talked about last time. The way in which electrons and holes spread out in the nanocrystals that we've discussed is shown here. So when you excite a cadmium selenide quantum dot, let's see here, comment. Thank you, Avery. So these are radial distribution functions of electrons in holes in cadmium selenide. At the top, cadmium selenide, cadmium sulfide heterostructures in the middle, and cadmium selenide, zinc sulfide heterostructures on the bottom. And you can see a couple of things, right? The electron is more delocalized than the hole. The hole is perfectly happy sitting in the cadmium selenide core, and it's not that confined. The electron runs into the edge of the crystal and drops off very rapidly. It is more strongly confined, and that makes sense because the electron and hole effective masses are different. So the electron moves around a lot more, moves more quickly, has a longer wavelength, and so you can see that there in the way the electron is spread out into the core of the crystal. And then the same thing happens when you have a heterostructure, but now when you have a cad sulfide shell around a cad selenide core, the electron spreads out into that shell. The hole does not. That separates the electron and hole and reduces their overlap. Zinc sulfide doesn't allow the electron to delocalize into the shell, or at least not to the same degree that cadmium sulfide does, more so than just the matrix. And so the electron and hole remain in the core, primarily in that cad selenide zinc sulfide core shell structure, unlike the cad selenide cad sulfide one. In addition to the effective masses, the other thing to consider are the offsets between the conduction bands where the electrons reside and the valence bands where the holes reside. That also has an influence on the extent to which the electron and hole spread out. And we talked about how the different types of band alignments in those materials give rise to a type 1 type of a band structure, which is the cad selenide zinc sulfide case, where the cad selenide valence and conduction bands fall within the zinc sulfide ones, whereas the cad selenide conduction band and the cadmium sulfide conduction band are at about the same energy, and so that's a quasi type 2 situation. We talked also about how in a cadmium selenide, cadmium sulfide core shell structure, the dimensions of that shell really influence how far away that electron delocalizes from the hole, and that changes the radiative probability. It also changes the photoluminescence quantum yield, and it changes the energy of the luminescence. So the degree of the electron confinement changes as you change that thickness, and that changes the exciton energy, which you can see there on the right. As the thickness gets larger, the luminescence spectrum redshifts. And it also changes the lifetime. So very thick shells where the electron and hole are very separate from one another and have a weak overlap, that slows down the recombination kinetics. So you can see that in that graph if you want to analyze it. Here's the PL intensity, or the number of luminescence events, and this measurement is a function of time. And this sample here, the luminescence lasts a longer time before it completely decays. This one, luminescence decays very rapidly. And you can see these are for different thicknesses. This one is for the thickest shell. Okay, so the dimensions of the particle influence the kind of confinement you get. That changes the electron hole overlap, and that changes the recombination. So Nanoparticles like this are really cool because you can tune their optical properties by adjusting the crystal. And that's very powerful. And the other example we talked about was a type 2 heterostructure. Now we're looking at cadmium selenide, cadmium telluride, and in that case, the band offset, let me see here. Yeah, in that case, the band offset looks like this, where the conduction and valence bands are kind of nested, or not nested, but staggered like that. And that staggered arrangement of conduction and valence bands means that the electron always transfers over to the cadmium selenide part, and the hole always transfers over the cadmium telluride part. And so you photoexcite the crystal, and then you get this exciton, and the two charges are in different regions, but they're kind of stuck to each other. You know, they're attracted to each other nonetheless. And then when it undergoes recombination, typically you see that recombination from this charge separated state, where one is on one side of the crystal and the other is on the other side. They're overlapping just enough where they still will do luminescence. And typically that luminescence is very slow to appear. So the excited state lifetimes are longer. And they, show some other characteristics like temperature dependence. Okay, so the material combination, the dimensions, all of that can be used to modify where the charges are, whether they separate or whether they undergo luminescence. And so you can tailor one of these materials for a particular application space. Just briefly, I'll also mention we didn't spend a lot of time talking about this, but the dimension that you confine the structure is the one that leads to energetic changes and density of states changes. So you can see densities of states diagrams for conduction and valence bands in the bulk on the left here. And as you confine it in one dimension and obtain a platelet, you get this sort of like stair-like structure, and you confine it in 2 dimensions and you get this spiky kind of a structure. Then finally you confine it in all 3 dimensions, and you end up with discrete levels, and those discrete levels are of course higher than the conduction and valence band edges of the bulk. Okay, so the energies of the lowest transitions in these materials is dominated by the narrowest dimension of the crystal. Okay, so today we're going to start talking a little bit more about exciton recombination, luminescence in particular. And I just want to remind you, of course, we've talked about monoexciton photoluminescence. So photoluminescence is a type of luminescence process. It's distinct from electroluminescence, where you pump in electrons and you get photons out. This is where you pump in photons and you get photons out. People often use the word fluorescence when talking about photoluminescence, but really what they mean, fluorescence has a specific meaning. It's associated with a spin state. Phosphorescence has a specific meaning associated with the spin state, but both phosphorescence and fluorescence processes can be examples of photoluminescence. Right? So photoluminescence is a more general term that refers to the excitation method. Just plain old luminescence also works. But anyway, so you excite the valence band electrons up into the conduction band, and the excess energy of the photon beyond the band gap is lost in a few picoseconds as the electron and the hole cool down to the valence band edges. And then you get this electron hole pair and that sort of has a minimum energy. And then within a nanosecond or a few microseconds, those electrons and holes recombine. And they can recombine radiatively, as is shown there on the left. And the energy of the photon that comes out is equal to that band gap spacing. Okay, so that's familiar. In quantum dots, actually, it's pretty common to also form other kinds of excitons, including biexcitons. So a biexciton is just a pair of electron hole pairs. So 4 excited charges. And, this happens all the time. It's not that hard to excite a quantum dot twice before it emits. people study what happens if you excite it 3 times or 4 times or 5 times or more. And, those kinds of photophysics are fun, and very important to applications like lasers, for example. Laser, if you have a bunch of emitters, what you're trying to do is to get the number of emitters in the excited state higher than the number in the ground state, which is what's called population inversion. And under those kinds of conditions, the concentration of excited states is really high, and it becomes very common to form bi-excitons. If you put a quantum dot onto an LED bulb, you're trying to take a blue LED and turn it into white light LED using quantum dots. The LED will excite the quantum dots more than once. And in fact, any kind of laser experiment, you have to turn the laser power down so you don't excite the quantum dots too much, and end up studying bi-excitons instead of mono-excitons. Another kind of a multiple exciton is a positive trion or a negative trion, and this can result when you have a nanocrystal that has an extra charge, and then you photoexcite it. Now you have 3 charges, and this photoexcited electron has 2 ways to recombine, or these pair of photoexcited electrons can recombine. Either one can recombine. So positive trions and negative trions form, and their recombination is different than a monoexciton. Okay, and all of those species are really very important to the behavior of nanocrystal quantum dots. All right. So just a brief introduction to Fermi's golden rule. Fermi's golden rule is a statement of, how you can predict parameters from 2 wave functions by looking at the coupling, and it's often used to talk about transition probabilities. Okay, so if you want to calculate the likelihood of an optical transition, you have to consider the overlap of the wave functions of the initial and the final states, and then the operator that acts on that overlap integral to determine the function of interest. And the function of interest here is the transition probability, or the radiative probability, or the probability of undergoing absorption. Okay, and so if you have an initial state and a final state, you look at that overlap of those 2 wave functions. If you have multiple final states, you consider the overlaps of all of those possible transitions, and then it's expressed as an energy or as units, as in per volume units. Okay, so this operator and this overlap here contain selection rules in them. So dipole transition strength is like one of the selection rules that you could put there, or sorry, one of the operators that you could put there. Okay, so orbital overlap is very important, or wave function overlap of the initial and final states is very important to the transition probability, and it influences things like the radiative rate. It also influences things like the absorption rate. I'll show you that in just one second, but before I forget, I want to say that this sum over all states thing is also very important when considering degeneracies in a wave function. So, the valence band of cadmium selenide is made up of p orbitals, and the conduction band is made up of s orbitals. And the p orbitals are triply degenerate, right? You have px, py, pz. So that gives rise to more degeneracy in the valence band than in the conduction band. And when doing these kinds of calculations, and you're looking at the initial and the final states, you have to add them up for all of those states, right? If there are multiple choices for recombination, you have to sum over all of them. So if the valence band is multifold degenerate, say 3-fold degenerate or something, times the number of electrons in those states, then the number of possible transitions will go up. And that's going to come back here in just a few slides. So as I said, this orbital overlap thing is important for the transition probability. And this is a size-dependent parameter. So I've taken a figure from a paper, the reference for which is not included here. But what it's done is it's plotted different cadmium selenide absorption spectra on top of each other. And out here at high energies, you'll see that the spectra all are very similar in terms of the magnitude of their overlap, or sorry, the magnitude of the extinction coefficient. So this is an extinction coefficient. It's an extinction coefficient expressed in thickness, which is how solids are treated. And it's saying for a given nanoparticle size and divided by the total amount of material, so we're comparing apples and apples here, out at high energy, you'll find that the transition probability, the absorption that you can get, is the same for all nanoparticles. Okay, it's not really that different. And as you go to lower and lower energies and you start getting into these excitonic states, and particularly the lowest energy excitonic transition, which is this bump that you see here, the intensity of that bump changes as a function of the size of the particle. So we're going to lower energies down here. So these spectra are for larger particles. This spectrum here is for the smallest particle in this series. And so for a given volume of material, the small particle's lowest energy optical transition is much more intense than the large particles. And that's because of orbital overlap, at least partly because of orbital overlap. In a small nanocrystal, the electron and hole have a higher concentration. Their wave functions are more strongly overlapping than in a large one. And so the intensity of this bump here is much higher than that one. Okay, so, for the sake of this class and in general, I think the important thing to remember is that the wave function overlap for the initial and final states really matters. And it's one of the ways you can calculate or estimate whether or not something is going to have a highly probable optical transition. So this is absorption, but photoluminescence and absorption are the inverse of each other and obey the same kinds of principles here. So you might expect a smaller nanocrystal to have a faster radiative process, luminescence process, than a large one for the exact same kind of reasons. All right, so let's take a look at radiative recombination of multi-excitons. So now a bi-exciton here, we've got two excited charges, two excited holes, we have a positive trion, a negative trion. All of these things can undergo radiative recombination. The electron can fall down, fill the hole in all three cases, and you can actually calculate, my goodness, you can actually calculate the number or the radiative process for each of these different states, the bi-exciton or the positive and negative trions, using this equation here. So if you know the radiative rate of the monoexciton, and then you consider the number of electrons and holes available to undergo recombination, you can calculate the radiative rate based on that single excitonic transition. So this should just be x and not 1x, but I guess it's the same. So this is the radiative rate of the monoexciton. If you wanted to take this value, then you could also calculate the radiative rate of the bi-exciton by just multiplying by the number of electrons and holes in the bi-excitonic state. So the bi-exciton has 4 electrons and 4 holes. The monoexciton has 1 electron and 1 hole. The bi-exciton has 2 electrons and 2 holes. So if you put 2 and 2 here, you get a 4 in front, and that tells you that the bi-exciton recombination rate, radiative rate, is going to be 4 times the monoexciton recombination rate. And then a trion has either 2 electrons and a hole or 1 electron and 2 holes. So that says that the trion rates are going to be twice the monoexciton rates. Okay, so there's in principle nothing special about a trion. It's just an extra charge, and that increases the number of ways the thing can recombine by a factor of 2. And the same is true of a biexciton. The number of charges is greater, and so the number of possible transitions is larger. And so it's true that these sort of relative magnitudes approximately hold. Now, let's take a look at Auger recombination. Auger recombination is different than radiative recombination. Auger recombination, and I've forgotten whether we've already introduced this now, but when you have a biexciton, like is shown up here in the upper left, you got 4 charges, and one of the kinds of transitions they can do is to combine a photoexcited electron with a hole, and instead of giving off the energy in making that transition as a photon, it will transfer that energy to an adjacent electron and photoexcite it. And of course, that excited electron very rapidly cools to the band edge, giving off phonons, just like we saw in this diagram here. You excite this electron and it falls back down and cools. Same thing happens in this case. You excite this electron, it'll just fall back down and cool. Trions can also do this. They have fewer options, but this electron can fall down and promote this hole. And promoting this hole means forcing a balloon full of air underwater. All right, so, and then of course that will very quickly float up to the surface, or the inverse here with the negative trion, recombine and excite. So Auger recombination is a very important process in semiconductor quantum dots, and it's really one of the dominant recombination mechanisms that determines whether or not the material is luminescent, as we'll see. You can estimate the probability of this transition here by doing counting statistics again. And it turns out one simple way to look at this is that this biexciton is kind of like a mixture of a positive trion state and a negative trion state. And so, if you consider that this electron can recombine with these 2 holes by promoting a hole, or this electron can recombine with one of these holes by promoting the other electron, you can then say that the probability of radiative recombination from the biexciton is the sum of those 2 pathways. Now, this arrow could be on the right-hand side or the left-hand side. So there's 2 ways to write out the negative trion and positive trion pathways. So the biexciton Auger recombination probability turns out to be twice the sum of those, which is in a world where these 2 are equal, the trion, negative and positive trion rates, this guy then is just 4 times the trion rate. Okay, so Auger recombination from a biexciton is about 4 times faster than Auger recombination from a negative trion. Now, these things also ignore the multifold degeneracy. So it turns out that the valence band and conduction band don't have the same degeneracy in many different materials, and so we would have to further modify this picture. So let's take a look at how this appears when you are actually doing an experiment. And what I've shown you here are a series of photoluminescence decay traces. So this is the intensity of photoluminescence with time. And what they're doing is actually increasing the laser power in this experiment. So they have a quantum dot, it's nice and luminescent. They're pumping it, and then they turn up the laser power so that the photoluminescence intensity, the illumination intensity, or the photon flux, is higher. Okay, and when they do that, what they see is this rapid decay at early times, and then a very slow decay that looks just like any one of these other traces. And the amount of this rapid decay at early times increases the higher you pump the thing. This is a signature of Auger recombination. In this experiment, as you're increasing the excitation intensity or the fluence, you're making higher and higher concentrations of biexcitons, and those biexcitons are recombining very rapidly by doing Auger recombination. Okay, Auger recombination turns out is about an order of magnitude or two faster than radiative recombination for reasons other than just simple counting statistics. Um, and uh, and you can see that if you play with the laser power. So you start creating higher and higher concentrations of these multi-excitons, and you start seeing their decay kinetics first, and then a much slower decay from a standard monoexciton. So for people have studied these Auger recombination problems for a long time because they, as you will see in a minute, determine the photoluminescence quantum yield, but they're also very important to lasers and light bulbs. And so, how does Auger recombination work in these materials? One of the things that has been found is that the lifetime of the excited states, either tryons or biexcitons, is strongly size dependent. Okay, and so I've plotted that data here for you. And this symbol tau refers to the lifetime. The lifetime is just the inverse of the rate constant for recombination. Okay, so a long lifetime has a low rate constant for recombination. And so here, this is on a log scale. You can see that the negative tryon lifetime is the longest. It's the least likely to underdo Auger recombination. The positive tryon is more likely to do Auger recombination. And then the biexciton is most likely to do Auger recombination. And that's true regardless of size. You can see that for the biexciton, the positive tryon, and the negative tryon, as the particle gets larger and larger and larger, the probability of the recombination drops. So a bigger particle has a longer Auger recombination lifetime. Notice the units here, picoseconds. So these are orders of magnitude faster than just radiative recombination. In any case, the larger the particle, the slower the Auger recombination. But even though you can see that's true, notice how very reliably the difference between the negative, positive, and biexciton recombination times evolve. They're all the same here for all of these different materials. And if you take this straight line and you look at those lifetimes as a function of radius, you'll find that it basically goes as radius cubed. So, this is a recombination probability that is proportional to the volume of space in which the recombination is happening. And that has a lot to do with the number of atoms in the crystal and the number of possible states that the either electron or hole can go into when it is photoexcited. So remember that the recombination mechanism of a biexciton by the Auger process involves dropping down here, but it also involves promoting an electron up here. And the number of possible states that you can get is partly related to how many atoms there are in the crystal. So it also is influenced by the overlap of the electron and hole. Which increases at small sizes, okay? But in the end, really, it's just proportional to volume. So, and the relative difference, minus, plus, and biexciton is derived from the statistical counting that we talked about on this page here. The number of possible pathways explains the differences between the minus, plus, and biexciton rates. Okay, the other thing here are biexciton lifetimes plotted as a function of size, and you can see these straight lines here, this band of biexciton recombination lifetimes. And the surprising thing about this is that it's relatively insensitive to the material. Silicon and lead sulfide and cadmium selenide, they basically have the exact same Auger recombination lifetimes, um, and follow the radius trend. And so it tells you that this Auger recombination stuff is really relatively insensitive to the material type or the band gap of the semiconductor, and it's really all about the volume of the material, which is a pretty cool result. All right, so let's talk for a moment about photoluminescence quantum yield and how that relates. So photoluminescence quantum yield is the ratio of the numbers of photons that you get out and the number of photons that you put in. So if the particles are absorbing photons and becoming photoexcited, what percentage of them come back out as luminescence? And so another way to express that is the ratio of the rate constants for the radiative and non-radiative, excuse me, where's my laser pointer? There we go. For the radiative and non-radiative processes involved. So it's just the radiative piece, which is the part where you care about, how many photons are produced, divided by all rates that consume those excited electrons, okay? So in this case, one of the things we're really interested in is the quantum yield for a biexciton. So you would plug in the relevant rate constants here. And you can look at you can simplify things knowing actually that the Auger recombination rate is orders of magnitude, about 2 orders of magnitude faster than the radiative rate for the biexciton. And so you can say this rate constant here is very, sorry, did I do this incorrectly? I'm a little bit confused by this all of a sudden here. Yeah, sorry, this is right. So if the rate constant for Auger recombination is much greater than the radiative one, then this isn't relevant to the denominator. So basically the quantum yield is about 4 times the ratio of the radiative rate constant for biexcitons and the radiative rate constant, the Auger recombination rate constant for biexcitons. Okay, now this is a big oversimplification of quantum yield in part because there are other non-radiative rates that we're actually not considering in this equation that we're going to talk about going forward. But that ratio, the radiative and the Auger rate is very important for dictating quantum yield in these kinds of materials. And so a lot of people have studied ways to modify that. That's kind of a hard and fast rule, but people would like to determine, what can I do to try and separately influence those 2 different rates. And this is maybe a little bit heavy material-wise, but so we'll just try and get the overarching points across here. One of the things that can be modified in these kinds of nanocrystals is the overlap of the initial and the final states. And there's 2 ways that people have done that. They've changed the electron hole overlap, and of course you can do that by making the material type 2. The type 2 material, the electron and hole separate from one another, and that changes the strength of their interaction and changes the rate constants. And then the last one, another one, is changing the interaction strengths of the electrons of the initial and final states in Auger recombination. And in that case, you can play fun games looking at the initial and final state of this extra electron that's consuming the excited energy. So, if you have this negative trion here and the electron is dropping down to fill the hole and transferring the energy to this third electron, the third electron is moving way up in energy to a higher energy state. And so you can, by modifying the nanocrystal, you can change the degree of that coupling. And that coupling then will influence the radiative probability. Okay, so one of the ways that my group has been pursuing, along with others, is actually grading the alloy, grading an alloy between cadmium selenide and cadmium sulfide. So we've talked about thickening the shell of cadmium sulfide to allow the electrons to separate from the holes. And that reduces the Auger recombination kinetics and also the radiative recombination kinetics. And you can also grade the interface between the two, okay? And this does a fun thing where by making the confinement potential around the hole in the middle of the crystal and the electrons that spread out over the crystal, by making it smooth versus, say, abrupt, where you have pure cadmium selenide with pure cadmium sulfide around it, you change the overlap between the initial wave function of this third electron and the final. Okay, so if this guy is kind of soft, has a soft confinement potential, then you get something like the red line here. And if it has a steep confinement potential, you get something like the blue line. Now, to really understand this, you have to understand what the y-axis means. This is a representation of the wave function broken out into different components. So if you made a linear combination of all of the different wavelengths, or of many different infinite numbers of wavelengths, and summed them up, you can recreate the wave function of the initial and final state that are drawn here. And what they're saying, what this diagram is saying, is that here, as you go to higher and higher values of momentum, the wavelength of the component that makes up that wave function gets shorter and shorter. Okay, and so an abrupt potential, which has very steep walls, like a particle in a box, or an infinite potential well, that wave function has to go to zero right at the edges of that well. And to make such a wave function, you need to have a lot of these high frequency components to build up that thing. And something with a smooth potential doesn't have that same situation. The wave function doesn't have to decay to zero right at the edges of the boundary. And so you can use lower frequency component waves to make it up. And the final state, this electron that's way up here in energy, which has a much higher wavelength, tends to be composed more of these high frequency components here. So the final state is this peak. And you can see that the abrupt interface has a greater degree of overlap with the final state than the smooth interface does. And so all that's saying is that the overlap integral that you use to calculate the radiative rate, according to Fermi's golden rule, is modified by changing the confinement potential of the electron. Okay, so graded alloys do Auger recombination more slowly than abrupt ones, and that changes the quantum yield. And you can see that in this plot here. This plot is comparing the biexciton and single exciton quantum yields. And the higher up you go, the more likely you are to see a biexciton luminesce. And that ratio then increases. And so these graded alloys, Victor Klimov, who's Mr. Quantum Photophysics, these graded alloys have proven to be really powerful for making extraordinarily luminescent materials, even when you're making biexcitons and trions and whatnot. All right, so that's a lot to swallow, and I don't really expect you to understand this very deeply. It is, however, a nice example of how you can use nanostructure to tune the properties of quantum dots and change rate constants for Auger recombination and make higher performance structures for lighting applications and for lasing and things of that nature. So we're going to transition a little bit away to consider coordination chemistry and how surfaces actually become important in this space. And so I show some familiar pictures here on the left of the various wave functions composed of linear combinations of atomic orbitals, p orbitals in this case, and rings. And then on the right, you can see an MO diagram for cadmium selenide, where we've combined the 5s functions and the selenium 4p functions to make up the conduction and valence band levels. And then I've shown example LUMOs for quantum dot here on the right, kind of showing how these orbitals look an awful lot like these orbitals do. And so we've talked a lot about this picture, and for a semiconductor, this kind of all hangs together relatively well. But one of the things that's not illustrated by this diagram are the orbitals that are found at the surfaces of those crystals. So if you consider, a typical cadmium selenide quantum dot might have 10 or 20 or 30 or 40% surface atoms. And those surface atoms don't have the same number of bonds. They have fewer bonding partners. Some of them only make 2 bonds to the underlying crystal. Sometimes they make 3. And so the molecular orbitals that you get when you make combinations of those surface atoms with the underlying lattice don't have the same orbital interaction strength, and they are not spread out in energy as much. Okay, and so surface atoms in these kinds of materials tend to have smaller splittings, and they can fall outside of the conduction and valence band and form surface electronic states. And those surface states are really important. They are the true HOMO and LUMO of a quantum dot or a semiconductor nanocrystal. You don't really see them very well because they don't seem to overlap very well. That people think about them as being localized. So for example, you can see this surface atom orbital state plotted here on the right. This state does not delocalize over the whole crystal. It's just localized down here, and the poor overlap means that the radiative transition or the absorption are very improbable. So surface states are dark. You don't see them in the absorption spectrum. You only see the band-to-band transitions, not the surface state derived transitions. Okay, so there are all of these hidden electronic states in these materials that really dominate properties, and including the photoluminescence quantum yield. So if you have a photoexcited electron in one of these crystals, it ends up having a choice whether it wants to fall back down and produce light by luminescence, or it can do something called trapping. And trapping is just a colloquial term for the electron falling into one of these surface states and being no longer delocalized, but instead localized. And those localized charges have an easier time falling back down by producing phonons instead of photons. So surface states will capture photoexcited charges and allow them to recombine and get back to the ground state by producing heat. Another type of trapping mechanism that might be a little bit funny here is, imagine if you have a surface selenium atom with 2 electrons, it can actually reduce the hull of the exciton before recombination happens. So this trapping is very important for quantum yield. And as we'll see here in the next lecture, the surface chemistry of the quantum dots influences these levels and can be used to change quantum yield. So ligand binding is very important to recombination dynamics for that reason. So let's just say you have a photoexcited quantum dot with a monoexciton in it, and it undergoes rapid hole trapping. Okay, so good old simple monoexciton, surface selenium electron pair ionizes and reduces this valence band hole, and now you end up with the situation where you have a valence band hole on a surface selenium, and you have an extra negative charge in the conduction band level. And if you excite that crystal, you end up with this kind of a multi-exciton, where you have 2 electrons in the conduction band, 1 in the valence band, and then this hole sitting on a surface atom. And you could also imagine some kind of external source of electrons rather than just a surface selenium atom dumping an electron onto the particle, and then you'd end up with this same sort of trion in the particle, but you wouldn't have the ionized surface state. Regardless, by putting that extra electron into the conduction band, you can suddenly turn on Auger recombination of this negative trion. Okay, so the Auger process starts turning on, and Auger recombination is orders of magnitude faster than, excuse me, than standard radiative recombination under normal conditions. Graded alloys can influence the probability of that Auger recombination and change whether or not that state undergoes luminescence. But in any case, this sort of charge transfer into the particle from a surface state leads to a metastable species that then does Auger recombination, and that Auger recombination competes with the photoluminescence. It becomes a non-radiative mechanism for recombination that erodes quantum yield. And so people for a long time have seen that this kind of charging actually is reversible. So you can excite a particle multiple times, it'll sit there and do luminescence just like a good old monoexciton should. And then all of a sudden, along comes an ionization process, and the charge transfers from a surface atom or an external donor, fills up that hole. And now, when you excite the electron again, or you excite the nanoparticle again, it actually has this trion state that then underdoes very rapid Auger recombination. And so, when that happens, when the thing ionizes, the particle goes from a normal luminescent configuration to a configuration where luminescence is not very likely. And so the particle stops luminescing. And then eventually that extra charge gets neutralized and the particle returns back to its original state. And suddenly it's luminescing again. And so this gives rise to intermittency or blinking of the photoluminescence. And so it turns out if you look at an individual quantum dot, you can see it turning on and off. Let's see if I can make this, look at that. So this is sort of a classic in blinking, I guess. I've seen this video many times before. You can see all these individual quantum dots in the field of view here, and they're not moving, they're just blinking, turning on and off. And sometimes you can even see ones that kind of go from being gray to bright and then back to gray again. Okay, so it sort of looks like starry night under a microscope. You see all of these particles flickering from their off state to their on state. All right, so if you take a look at a single nanoparticle in one of those images, you can plot the rate at which it's luminescing, the brightness of that spot versus time. And you'll get one of these traces like the one shown here, where the luminescence is jumping up and down. There are periods of time where it's steadily luminescing and periods of time where it's not luminescing at all. There are some periods of time where it's luminescing a little bit, half as much as usual, or really not much at all, but it is still, luminescent. So if you count up all these different events, then you can categorize this thing in terms of, how it is intermittent, okay, what its blinking characteristics are like. So it's thought that this kind of behavior arises from this charging and discharging type of a picture, but I'll tell you that there's a lot of debate about it. And one of the reasons there's a lot of debate is that it's very hard to know the structures of the crystals that are in these various states. You can measure other properties about them, but to really know anything about the structures is difficult. And so it's been difficult to give a chemical explanation for what is causing this kind of thing. All right, so Viktor Klimov, among many others, has taken these streams of photons and they've said, okay, well, if I break this thing down into its components, there's the case where the thing is emissive, and it's just emissive at this constant level that's very high. And, I'm going to say that is the monoexciton. And then there's cases where it's emissive, and it's only emissive at this particular level here. And then there's also cases where it's really not very emissive at all. It's essentially totally dark. And he bins those into different boxes, and using some microscopy tricks actually can look at the decay kinetics of each of those different bins. And he can break the decay kinetics down. So for the very brightly emissive states, you see recombination kinetics that are slow. For the ones that are kind of intermediate, gray states, as they call them, they're faster, but still slower than the ones that are very dim. So the ones that are very dim, the luminescence barely lives at all. It's very short-lived. And so it's telling you that each of these different species here has some competing process that they can undergo uh, uh, that is inducing this Auger recombination. And so Klimov says these two different gray states arise from negative trion and positive trion recombination. And then there's also a little bit of biexciton formation in there. And so he partly knows this because they have independently measured these individual rates, and so they have a rough idea about how fast each of those different materials does luminescence, each of those different excitonic states does luminescence. And so this decomposition into these various states, mono and multi-exciton states, becomes possible. In any case, what's important to recognize is that a quantum dot is not simple in this sense. It is not like a molecule in this sense. You can excite it multiple times. There are multiple different emissive states, and each of those emissive states has a different structure. And so when you look at the luminescence coming out of a quantum dot, sample of them, it's not like a molecule. Okay, multiple different emissive states are acting, and they're changing back and forth with time in this way that gives rise to blinking. Okay, and so one of the things that many people have been doing is looking at what dictates this blinking. And one of the things that's been found is that, if you play around with the shell dimensions, you can influence the magnitude of the degree to which the nanoparticle undergoes blinking. So on the bottom here, this bottom blinking trace shows a nanoparticle with a thin shell. And on the top, you see one with a thick shell. And if you take all of the points on this plot spread out in time and you bin them together, you can look at the intensity, the probability of having emission at this intensity versus, say, that one. And you can see really there's only a little bit of material, or only a little bit of the time do you see particles falling into this bin here and luminescing in this sort of gray kind of a way. And then if you make a thinner shell, you'll find that the ratios change, and the number of, and the distinct type of emissive states evolves. Okay, and so these different shell thicknesses are saying something about the rates of Auger recombination from biexcitons and trions in these materials. They're also saying something about the concentration of those. So again, tuning composition changes performance. The material on the top is far more likely to have a bright photoluminescence quantum yield than the one on the bottom, simply because the concentration of nanoparticles in their on state is high. And the ones down here, the concentration of the nanoparticles that are in their on state is not as high. So, okay. Another thing that happens actually, or is thought to be important, is that if you make a biexciton and now it has this choice between undergoing photoluminescence and Auger recombination, that can, which way it goes, can also induce other changes, one of which is the probability of ionization. Okay, so let's say you make a biexciton and then a biexciton does Auger recombination, and now you get this photoexcited electron that's way up high in energy. In a material like cadmium selenide, this Auger recombination diagrammed here would give you an electron that almost has enough energy to just be emitted, like arc out of the particle, okay? So an electron with all that excess energy stored in it is very good at doing ionization chemistry and reactions like, the reduction of dioxygen, for example. So it's thought that the formation of these biexcitons can actually induce ionization, which leads to tryons. And now you have a tryon with a missing electron, and that positive tryon does Auger recombination. And so generating biexcitons can lead to the formation of tryons and can cause particles to go dark. And so one of the things that you'll see actually is that in a particle with time, you're exciting it. And if you're exciting it at a relatively high energy, with a high intensity, that you'll start building up a concentration of these negatively charged or positively charged particles. And the luminescence quantum yield will actually change with time. And in fact, some of the time, this leads to brightening of the sample. So the nanoparticle or the quantum yield for luminescence actually increases at early times, and then it starts to decay. And then if you turn off the excitation source, it'll actually kind of repair itself and return to some value that it started at before, for example. Okay, and so the photoluminescence quantum yield, the probability for emission from these materials can evolve with time as they undergo these charging events. All right, so quantum yield is complicated. A lot of people come to me and say, hey, I started working with nanoparticles and I saw that the quantum yield changed when I added something to them. I was thinking about studying that process, and I often have to explain that this stuff is really complicated and people do not understand it very well. There's no structural assignments, and the possible photophysical mechanisms behind the luminescence decay are diverse, and dissecting them is really difficult. So that's a pretty hairy area of science. There's a lot of stuff going on there. But very, very interesting nonetheless, especially for showing off all the different photophysical mechanisms behind those kinds of processes. And, also to illustrate that there's a lot of potential to tune those behaviors and improve them, to shut down Auger recombination by reducing the overlap with this third electron or third hole that facilitates Auger recombination from the tryon. If you want to make a laser out of quantum dots, or you want to make a solid state light bulb with quantum dots, you have to get good at modifying those kinds of processes to optimize those materials. All right, so let's just walk through some conclusions on this material here. So we talked about how electronic transitions depend upon selection rules, all the way back to what is a direct bandgap semiconductor, what's an indirect bandgap semiconductor, and how that relates to the transition dipole. But it also depends upon the overlap of the initial and final states and the number of initial and final states. You have to consider how many possible transitions there are to know how fast overall that type of a reaction, say Auger from a biexciton, how fast that is going to be. And you can just do simple counting to come up with a very good estimate of the relative and magnitude of those types of processes. Auger recombination is much faster than monoexciton recombination for statistical reasons, for orbital overlap reasons. And so Auger recombination is very important in small quantum dots. It has a really big impact on their performance. And it's those rates are all tunable with the dimensions of the particle. So, you make a bigger particle, you slow them down, you change the electron and hole confinement, you change their overlap, you change their overlap with the final states during Auger recombination, and suddenly, you can just fiddle around and control things just by growing different kinds of crystals. We provided this example of the graded alloys providing a soft confinement potential. The soft confinement changes the overlap of the initial and the final states for the third charge. In any case, all of those are great examples of how tunable these materials are. And then we introduced blinking and talked about some of the characteristics of blinking. Blinking is really a consequence of Auger recombination. You form those trions, and the trions don't have the same recombination kinetics. They're much faster to recombine, and the recombinations are non-radiative. So you get into a trion, and suddenly the material is not very luminescent, and so ionization of the particle is one of the ways that happens, um, um, and gives rise to these blinking traces.